Hello friends, so going to start this book, Hands-on Machine Learning with Scikit-Learn, Keras and TensorFlow third edition. So going to start it.
Hands-on machine learning with Scikit-Learn, Keras and TensorFlow concepts, tools and techniques to build intelligent systems, TM. Hands-on machine learning with Scikit-Learn, Keras, and TensorFlow. Through a recent series of breakthroughs, deep learning has boosted the entire field of machine learning. Now, even programmers who know close to nothing about this technology can use simple, efficient tools to implement programs capable of learning from data. This best-selling book uses concrete examples, minimal theory, and production-ready Python frameworks to help you gain an intuitive understanding of the concepts and tools for building intelligent systems. With this updated third edition, author Aurélien Géron explores a range of techniques, starting with simple linear regression and progressing to deep neural networks. Numerous code examples and exercises throughout the book help you apply what you've learned. Programming experience is all you need to get started. Use Scikit-Learn to track an example ML project end-to-end. Explore several models, including support vector machines, decision trees, random forests, and ensemble methods. Exploit unsupervised learning techniques such as dimensionality reduction, clustering, and anomaly detection. Dive into neural net architectures, including convolutional nets, recurrent nets, generative adversarial networks, autoencoders, diffusion models, and transformers. Use TensorFlow and Keras to build and train neural nets for computer vision, natural language processing, generative models, and deep reinforcement learning. An exceptional resource to study machine learning. You will find clear-minded, intuitive explanations, and a wealth of practical tips. François Chollet, author of Keras, author of Deep Learning with Python. It's a great introduction to the theory and practice of solving problems with neural networks. I recommend it to anyone interested in learning about practical ML. Pete Warden, mobile lead for TensorFlow. Aurélien Géron is a machine learning consultant. A former Googler, he led YouTube's video classification team from 2013 to 2016. He was also a founder and CTO of Wireless ISP in France in 2001, a telecom consulting firm.
Okay, you can see the price is $80 US. Okay, going to start from here.
To 198, tools and techniques to build intelligent systems. Aurélien Géron. Hands-on machine learning with Scikit-Learn, Keras, and TensorFlow by Aurélien Géron. Copyright.
Aurélien Géron. Okay, now you can see from here. You can see table of contents. Okay, table of contents. You can see the fundamental of machine learning part 1. And then end-to-end machine learning project, you can see here. That's great, really great. And then classification, training models, support vector machines, decision tree, unsupervised learning, and random forest. And dimensionality reduction, and unsupervised learning techniques. Then part 2 is neural network and deep learning, introduction to artificial neural networks with Keras. Okay, training deep neural networks, custom models, and training with TensorFlow, loading and pre-processing data with TensorFlow, deep computer vision using conventional neural networks. You can see here, processing sequences using RNNs and CNNs, natural language processing with RNNs and attention. Okay, and autoencoders, GANs, and diffusion models. You can see reinforcement learning, and training and deploying TensorFlow models as well. You can see all these topics. Machine learning project checklist. You can see autodiff, special data structure, TensorFlow graphs, and index. So total 811 pages are there. So starting from the page number, so before starting page number 1, let's start preface. Okay.
Preface. The Machine Learning Tsunami. In 2006, Geoffrey Hinton and others published a paper showing how to train a deep neural network capable of recognizing handwritten digits with state-of-the-art precision. They branded this technique deep learning. A deep neural network is a simplified model of our cerebral cortex composed of a stack of layers of artificial neurons. Training a deep neural net was widely considered impossible at the time, and most researchers had abandoned the idea in the late 1990s. This paper revived the interest of the scientific community, and before long, many new papers demonstrated that deep learning was not only possible, but capable of mind-blowing achievements that no other machine learning technique could hope to match. This enthusiasm soon extended to many other areas of machine learning. A decade later, machine learning had conquered the industry, and today it is at the heart of much of the magic in high-tech products, ranking your web search results, powering your smartphone's speech recognition, recommending videos, and perhaps even driving your car.
Yes.
Machine learning in your projects. So, naturally you are excited about machine learning and would love to join the party. Perhaps you would like to give your homemade robot a brain of its own, make it recognize faces, or learn to walk around. 1. Geoffrey E. Hinton et al. A fast learning algorithm for deep belief nets. Neural computation, 1554. 2. Despite the fact that Yann LeCun's deep convolutional neural networks had worked well for image recognition, although they were not as generative data. With machine learning, you could accomplish the following and much more. Segment customers and find the best marketing strategy for each group. Recommend products for each client based on what similar clients bought. detect which transactions are likely to be fraudulent, forecast next year's revenue. Whatever the reason, you have decided to learn machine learning and implement it in your projects. Great idea, objective and approach. This book assumes that you know close to nothing about machine learning. Its goal is to give you the concepts, tools, and intuition you need to implement programs capable of learning from data. We will cover a large number of techniques, from the simplest and most commonly used to some of the deep learning techniques that regularly win competitions. For this, we will be using production-ready Python frameworks. Scikit-Learn is very easy to use, yet it implements many machine learning algorithms efficiently, so it makes for a great entry point to learning machine learning. It was created by David Cornepo in 2007 and is now led by a team of researchers at the French Institute for Research in Computer Science and Automation. TensorFlow is a more complex library for distributed numerical computation. It makes it possible to train and run very large neural networks efficiently by distributing the computations across potentially hundreds of multi-GPU servers. TensorFlow was created at Google and supports many of its large-scale machine learning applications. It was open-sourced in November 2015, and version 2 was released in September 2017, and version API that makes it very simple to train and run neural networks. Keras comes bundled with TensorFlow, and it relies on TensorFlow for all the intensive computations. The book favors a hands-on approach, understanding of machine learning through concrete working examples and just a little bit of theory.
Yeah.
While you can read this book without picking up your laptop, I highly recommend you experiment with the code examples. Code examples. All the code examples in this book are open source and available online at hub.com Géron HandsonML as Jupyter notebooks. These are interactive documents containing text, images, and executable code snippets. The easiest and
Okay, sorry for interpreting, but I want to see this link. What I can do?
all the code examples in this book are open source and
1 minute. Okay, let me. Okay, fine. Start it.
available online at hub.com Géron HandsonML as Jupyter notebooks. These are interactive documents containing text, images, and executable code snippets. The easiest and quickest way to get started is to run these notebooks using Google Colab. This is a free service that allows you to run any Jupyter notebook directly online without having to install anything on your machine. All you need is a web browser and a Google account. In this book, I will assume that you are using Google Colab, but I've also tested the notebooks on other online platforms such as Kaggle and Binder, so you can use those if you prefer. Alternatively, you can install the required libraries and tools and run the notebooks directly on your own machine. See the instructions at. This book is here to help you get your job done. If you wish to use additional content beyond the code examples, and that use falls outside the scope of fair use guidelines, please reach out to us for permission at permissions@o'reilly.com. We appreciate, but do not require, attribution. An attribution usually includes the title, author, publisher, and ISBN. Hands-on Machine Learning with Scikit-Learning and TensorFlow by Aurélien Géron. Copyright 2023 Géron, Keras, and TensorFlow by Requisites. This book assumes that you have some Python yet. The official tutorial on python.org is also quite good. This book also assumes that you are familiar with Python's main scientific libraries, in particular, NumPy, Pandas, and Matplotlib. If you have never used these libraries, don't worry, they're easy to learn, and I've created a tutorial for each of them. You can access them online at. Moreover, if you want to fully understand how the machine learning algorithms work, then you should have at least a basic understanding of a few math concepts, especially linear algebra. Specifically, you should know what vectors and matrices are, and how to perform some simple operations like adding vectors, or transposing and multiplying matrices. If you need a quick introduction to linear algebra, I provide a tutorial at Tutorials. You will also find a tutorial on differential calculus.
Okay, I will check out each tutorial after completing this first chapter of this book, because my target is to complete first chapter and some part of the second chapter. That's my target for today. So after completing that target, I will also see the tutorial, watch the tutorial, and understand the concepts. Okay, so continuing the lecture, continuing this book reading.
Which may be helpful to understand how neural networks are trained, but it's not entirely essential to grasp the important concepts. This book also uses other mathematical concepts occasionally, such as exponentials and logarithms, a bit of probability theory, and some basic statistics concepts, but nothing too advanced. If you need help on any of these, please check out, which offers many excellent and free math courses online. Roadmap. This book is organized in 2 parts. Part Y, the fundamentals of machine learning, covers the following topics: what machine learning is, what problems it tries to solve, and the main categories and fundamental concepts of its systems. The steps in a typical machine learning project: learning by fitting a model to data, optimizing a cost function, handling, cleaning, and preparing data, selecting and engineering features, selecting a model, and tuning hyperparameters using cross-validation. The challenges of machine learning, in particular underfitting and overfitting. The most common learning algorithms: linear and polynomial regression, logistic regression, k-nearest neighbors, support vector machines, decision trees, random forests, and ensemble methods. Reducing the dimensionality of the training data to fight the curse of dimensionality. Other unsupervised learning techniques, including clustering, density estimation, and anomaly detection. Part 2, Neural Networks and Deep Learning, covers the following topics: what neural nets are and what they're good for, building and training neural nets using TensorFlow and Keras, the most important neural net architectures, feed-forward neural nets for tabular data, convolutional nets for computer vision, recurrent nets, and long short-term memory nets for sequence processing, encoder-decoders and transformers for natural language processing, autoencoders, generative adversarial networks, and diffusion models for generative learning. Techniques for training deep neural nets. How to build an agent that can learn good strategies through trial and error, using reinforcement learning, loading and pre-processing large amounts of data efficiently. Training and deploying TensorFlow models at scale. The first part is based mostly on Scikit-Learn, while the second part uses TensorFlow and Keras. Don't jump into deep waters too hastily. While deep learning is no doubt one of the most exciting areas in machine learning, you should master the fundamentals first. Moreover, most problems can be solved quite well using simpler techniques such as random forests and ensemble methods. Deep learning is best suited for complex problems such as image recognition, speech recognition, or natural language processing, and it requires a lot of data, computing power, and patience. Changes between the first and the second edition. If you have already read the first edition, here are the main changes between the first and the second edition. All the code was migrated from TensorFlow 1.x to TensorFlow 2x, and I replaced most of the low-level TensorFlow code with much simpler Keras code. The second edition introduced the Data API for loading and pre-processing large datasets, the Distribution Strategies API to train and deploy TF models at scale, TF Serving in Google Cloud AI Platform to productionize models, and TF Transform, TF Lite, TF Add-in SEQ TensorFlow JS, and TF Agents. It also introduced many additional ML topics, including a new chapter on unsupervised learning, computer vision techniques for object detection and semantic segmentation, handling sequences using convolutional neural networks, natural language processing using recurrent neural networks, CNNs and transformers, GANs, and more. See for more details. Changes between the second and the third edition. If you read the second edition, here are the main changes between the second and the third edition. All the code was updated to the latest library versions. In particular, this third edition introduces many new additions to Scikit-Learn. It also introduces the Keras tuner library for hyperparameter tuning, Hugging Face's transformers library for natural language processing, and Keras's new pre-processing and data augmentation layers. Several vision models were added, as well as guidelines for choosing the right one. Chapter 15 now analyzes the Chicago bus and rail ridership data instead of generated time series, and introduces the ARMA model and its variants. Chapter 16 on natural language processing now builds an English to Spanish translation model, first using an encoder-decoder RNN, then using a transformer model. The chapter also covers language models such as switch transformers, Distilbert, T5, and PLM. In addition, it introduces vision transformers and gives an overview of a few transformer-based visual models, such as data-efficient image transformers, Perceiver, and Dino, as well as a brief overview of some large multimodal models, including Clip, DAL, Flamingo, and Gato.
Yeah.
Chapter 17 on generative learning now introduces diffusion models and shows how to implement a denoising diffusion probabilistic model from scratch. Chapter 19 migrated from Google Cloud AI Platform to Google Vertex AI and uses distributed Keras tuner for large-scale hyperparameter search. The chapter now includes TensorFlow JS code that you can experiment with online. It also introduces additional distributed training techniques, including pipe dream and pathways. In order to allow for all the new content, some sections were moved online, including installation instructions, kernel principal component analysis, mathematical details of Bayesian Gaussian mixtures, TF agents, and former appendices A, C, and E, C. For more details, other resources. Many excellent resources are available to learn about machine learning. For example, Andrew N. Jing's ML course on Coursera is amazing, although it requires a significant time investment.
I am investing the time for this course. Currently, I am doing this course, Andrew Ng's ML course on Coursera. Very excellent course. I'm learning a lot and a lot of practical applications. Lab are also there. You can practice a lot. This course is excellent. You can do it by yourself. Okay, I'm continuing the reading.
There are also many interesting websites about machine learning, including Scikit-Learn's exceptional user guide. You may also enjoy DataQuest, which provides very nice interactive tutorials, and ML blogs such as those listed on Quora. There are many other introductory books about machine learning. In particular, Joel Gruss's Data Science from Scratch, 2nd edition, presents the fundamentals of machine learning and implements some of the main algorithms in pure Python. Stephen Marsland's Machine Learning, an Algorithmic Perspective, 2nd edition, is a great introduction to machine learning, covering a wide range of topics in depth with code examples in Python. Sebastian Roschke's Python Machine Learning, 3rd edition, is also a great introduction to machine learning and leverages Python open source libraries. François Chollet's Deep Learning with Python, 2nd edition, is a very practical book that covers a large range of topics in a clear and concise way, as you might expect from the author of the excellent Keras library.
Yeah.
It favors code examples over mathematical theory. Andrei Burkov's 100-page machine learning book is very short but covers an impressive range of topics, introducing them in approachable terms without shying away from the math equations. Yasser Sabu Mostafa, Malik Magdani Smail, and Xuan Tian Lin's Learning from Data is a rather theoretical approach to ML that provides deep insights, in particular on the bias-variance trade-off. Stuart Russell and Peter Norvig's Artificial Intelligence, A Modern Approach, 4th edition, is a great book covering an incredible amount of topics, including machine learning. It helps put ML into perspective.
Yeah.
Jeremy Howard and Sylvain Gugger's Deep Learning for Coders with FastAI and PyTorch provides a wonderfully clear and practical introduction to deep learning using the FastAI and PyTorch libraries. Finally, joining ML competition websites such as Kaggle.com will allow you to practice your skills on real-world problems, with help and insights from some of the best ML professionals out there. Conventions used in this book. The following typographical conventions are used in this book. Italic indicates new terms, URLs, email addresses, file names, and file extensions. Constant width. Used for program listings, as well as within paragraphs to refer to program elements such as variable or function names, databases, data types, environment variables, statements, and keywords. Constant width bold. Shows commands or other text that should be typed literally by the user. Constant width italic. Shows text that should be replaced with user-supplied values, or by values determined by context. Punctuation. To avoid any confusion, punctuation appears outside of quotes throughout the book. My apologies to the purists. This element signifies a tip or suggestion. This element signifies a general note. O'Reilly Online Learning. For more than 40 years, O'Reilly Media has provided technology and business training, knowledge, and insight to help companies succeed. Our unique network of experts and innovators share their knowledge and expertise through books, articles, and our online learning platform. O'Reilly's online learning platform gives you on-demand access to live training courses, in-depth learning paths, interactive coding environments, and a vast collection of text and video from O'Reilly and 200 plus other publishers. For more information, visit how to contact us.
You can
Please
contact
address
them.
comments and questions concerning this book to the publisher.
Okay, you can contact them. The address is given, email is given, and LinkedIn and Twitter and YouTube, all things are given. You can contact. Now starting from acknowledgements. Okay.
Acknowledgements.
Okay.
Never in my wildest dreams did I imagine that the first and second editions of this book would get such a large audience. I received so many messages from readers, many asking questions, some kindly pointing out errata, and most sending me encouraging words. I cannot express how grateful I am to all these readers for their tremendous support. Thank you all so very much. Please do not hesitate to file issues on GitHub if you find errors in the code examples, or to submit errata if you find errors in the text. Some readers also shared how this book helped them get their first job, or how it helped them solve a concrete problem they were working on. I find such feedback incredibly motivating. If you find this book helpful, I would love it if you could share your story with me, either privately or publicly. Huge thanks as well to all the wonderful people who offered their time and expertise to review this third edition, correcting errors, and making countless suggestions. This edition is so much better thanks to them. Olga Zakpambetov, George Bonner, Francois Cholet, Sita Ganjou, Sam Goodman, Matt Harrison, Sasha Sobran, Louis Tunstall, Leandro Von Wera, and my dear brother Sylvain.
Yeah.
Fifth, I am also very grateful to the many people who supported me along the way, by answering my questions, suggesting improvements, and contributing to the code on GitHub, in particular, Yannick Asogba, Ian Beauregard, Ulf Bisport, Rick Chow, Parrots Cohen, Kyle Gallatin, Hannes Hapke, Victor Kaustov, Sunsun Kwan, Eric Lebegat, Jason Mays, Lawrence Maroney, Sarah Robinson, Joaquin Ruelas, and Yufeng Zhou. This book wouldn't exist without O'Reilly's fantastic staff, in particular Nicole Tache, who gave me insightful feedback and was always cheerful, encouraging, and helpful. I could not dream of a better editor. Big thanks to Michelle Cronin as well, who cheered me on through the final chapters and managed to get me past the finish line. Thanks to the whole production team, in particular Elizabeth Kelly and Kristen Brown. Thanks as well to Kim Kofer for the thorough copy editing, and to Johnny O'Toole, who managed the relationship with Amazon and answered many of my questions. Thanks to Kate D'Elia for greatly improving my illustrations. Thanks to Marie Bogiro, Ben Lorica, Mike Lukids, and Laurel Ruma for believing in this project and helping me define its scope. Thanks to Matt Hacker and all of the Atlas team for answering all my technical questions regarding formatting, ASCII-Doc, MathML, and LATX. And thanks to Nick Adams, Rebecca Demarest, Rachel Head, Judith McConville, Helen Monroe, Karen Montgomery, Rachel Rumeliotis, and everyone else at O'Reilly who contributed to this book. I'll never forget all the wonderful people who helped me with the first and second editions of this book, friends, colleagues, experts, including many members of the TensorFlow team. The list is long. Oljas Akbambetov, Carmel Allison, Martin Andrews, David Andrzejewski, Paige Bailey, Lucas Bewald, Sven Rusto, William Sargent, Francois Cholet, Clement Corbet, Robert Crow, Mark Daoust, Daniel Wolf Dobson, Julian Dubois, Matthias Kende, Daniel Kitacheski.
You can see all the
Their insatiable curiosity was priceless, explaining some
all the authors you can see. Okay.
Last
Lot
but
of
not
names.
least, I'm infinitely grateful to my beloved wife, Emmanuelle, and to our three wonderful children, Alexandra, Remy, and Gabrielle, for encouraging me to work hard on this book. Their insatiable curiosity was priceless, explaining some of the most difficult concepts in this book to my wife and children, helped me clarify my thoughts, and directly improved many parts of it. Plus, they keep bringing me cookies and coffee. Who could ask for more?
Yeah.
The Fundamentals of Machine Learning. Chapter 1. The Machine Learning Landscape. Not so long ago, if you had picked up your phone and asked it the way home, it would have ignored you, and people would have questioned your sanity. But machine learning is no longer science fiction. Billions of people use it every day. And the truth is it has actually been around for decades in some specialized applications, such as optical character recognition. The first ML application that really became mainstream, improving the lives of hundreds of millions of people, took over the world back in the 1990s. The spam filter. It's not exactly a self-aware robot, but it does technically qualify as machine learning. It has actually learned so well that you seldom need to flag an email as spam anymore. It was followed by hundreds of ML applications that now quietly power hundreds of products and features that you use regularly. Voice prompts, automatic translation, image search, product recommendations, and many more. Machine learning start, and where does it end? What exactly does it mean for a machine to learn something? If I download a copy of all Wikipedia articles, has my computer really learned something? Is it suddenly smarter? In this chapter, I will start by clarifying what machine learning is and why you may want to use it.
Yeah.
Then, before we set out to explore the machine learning continent, we will take a look at the map and learn about the main regions and the most notable landmarks, supervised versus unsupervised learning and their variants, online versus batch learning, instance-based versus model-based learning. Then we will look at the workflow of a typical ML project, discuss the main challenges you may face, and cover how to evaluate and fine-tune a machine learning system. This chapter introduces a lot of fundamental concepts that every data scientist should know by heart. It will be a high-level overview, all rather simple, but my goal is to ensure everything is crystal clear to you before we continue on to the rest of the book. So grab a coffee and let's get started. If you are already familiar with machine learning basics, you may want to skip directly to chapter 2. If you are not sure, try to answer all the questions listed at the end of the chapter before moving on. What is machine learning? Machine learning is the science of programming computers so they can learn from data. Here's a slightly more general definition. field of study that gives computers the ability to learn without being explicitly programmed. Arthur Samuel, 1959. And a more engineering-oriented one. A computer program is said to learn from experience E with respect to some task T and some performance measure P, if its performance on T, as measured by P, improves with experience E. Tom Mitchell, 97. Your spam filter is a machine learning program that, given examples of spam emails and examples of regular emails, can learn to flag spam. The examples that the system uses to learn are called the training set. Each training example is called a training instance. The part of a machine learning system that learns and makes predictions is called a model. Neural networks and random forests are examples of models. In this case, the task T is to flag spam for new emails, the experience E is the training data, and the performance measure P needs to be defined, for example.
You can see in this case the task T. I can decrease the speed so you can understand it well. Okay.
In this case, the task T is to flag spam for new emails, the experience E is the training data, and the performance measure P needs to be defined, for example. You can use the ratio of correctly classified emails. This particular performance measure is called accuracy, and it is often used in classification tasks. If you just download a copy of all Wikipedia articles, your computer has a lot more data, but it is not suddenly better at any task. This is not machine learning.
Yeah.
Why use machine learning? Consider how you would write a spam filter using traditional programming techniques. 1. First, you would examine what spam typically looks like. You might notice that some words or phrases tend to come up a lot in the subject line. Perhaps you would also notice a few other patterns in the sender's name, the email's body, and other parts of the email. 2. You would write a detection algorithm for each of the patterns that you noticed, and your program would flag emails as spam if a number of these patterns were detected. 3. You would test your program and repeat steps 1 and 2 until it was good enough to launch. Figure 1-1. The traditional approach, since the problem is difficult, your program will likely become a long list of complex rules, pretty hard to maintain. In contrast, a spam filter based on machine learning techniques automatically learns which words and phrases are good predictors of spam by detecting unusually frequent patterns of words in the spam examples compared to the ham examples. The program is much shorter, easier to maintain, and most likely more accurate. Figure 1-2, the machine learning approach.
1 minute. I have to stop. So here you can see the machine learning approach. How the machine learning is done. The approach is that first study the problem, starting from the problem, then train your machine learning model. That model you have to train through data. This is data, and on data you have to train your machine learning model. Then evaluate, and then launch it. And if it's some problem, then analyze the error. What the errors are there? Then again study the problem. Again train the machine learning model on the data, then evaluate, and then again if the error is done, then analyze the error, then again study the problem, train the machine learning model on the data, and evaluate. In the finally, if succeed, then just launch it. Okay, this is the machine learning approach.
What if spammers notice that all their emails containing for you are blocked? They might start writing for you instead. A spam filter using traditional programming techniques would need to be updated to flag for you emails. If spammers keep working around your spam filter, you will need to keep writing new rules forever. In contrast, a spam filter based on machine learning techniques automatically notices that for you has become unusually frequent in spam flagged by users, and it starts flagging them without your intervention. Figure 1-3. Automatically adapting to change another area. Where machine learning shines is for problems that either are too complex for traditional approaches.
Okay, you can see this is automatically adapting to the changes. You can see you don't have to suppose here what we are doing, we are updating again and again, making new rules forever. So what we can do at automatic adapting system in which the machine will automatically adapt the system. So you can see the first train machine learning model, then evaluate, and then launch, and then update data. If any data is updated, then again train on the data, and then train machine learning model, then evaluate, and then launch. Okay, fine.
Automatically adapting to change another area. Where machine learning shines is for problems that either are too complex for traditional approaches or have no known algorithm. For example, consider speech recognition. Say you want to start simple and write a program capable of distinguishing the words 1 and 2. You might notice that the word 2 starts with a high-pitched sound, so you could hard-code an algorithm that measures high-pitched sound intensity and use that to distinguish 1s and 2s, but obviously, this technique will not scale to thousands of words spoken by millions of very different people in noisy environments and in dozens of languages. The best solution is to write an algorithm that learns by itself, given many example recordings for each word. Finally, machine learning can help humans learn. ML models can be inspected to see what they have learned. For instance, once a spam filter has been trained on enough spam, it can easily be inspected to reveal the list of words and combinations of words that it believes are the best predictors of spam. Sometimes this will reveal unsuspected correlations or new trends, and thereby lead to a better understanding of the problem. Digging into large amounts of data to discover hidden patterns is called data mining, and machine learning excels at it. Figure 1-4.
You can see the figure 1/4. Machine learning can help humans learn. Okay, you can see how you can see first you study the problem, then train the machine learning model on the lots of data. On lots of data you will train, and then you will get solution and inspect the solution. Just check it the solution, or then you will get idea, better understanding of the problem, and repeat if needed. Otherwise, it's your choice. Okay.
Machine learning can help humans learn to summarize. Machine learning is great for problems for which existing solutions require a lot of fine-tuning or long lists of rules. Complex problems for which using a traditional approach yields no good solution. Fluctuating environments. Getting insights about complex problems and large amounts of data. Examples of applications. Let's look at some concrete examples of machine learning tasks, along with the techniques that can tackle them. Analyzing images of products on a production line to automatically classify them. This is image classification, typically performed using convolutional neural networks, or sometimes transformers. Detecting tumors in brain scans. This is semantic image segmentation, where each pixel in the image is classified, typically using CNNs or transformers.
You can see here analyzing images of products on a product line to automatically classify them. This is a very great application of machine learning. This is image classification typically performed using conventional neural network CNN. You will study more about it on chapter number 14. Or sometimes transformers, chapter number 16. Okay, detecting tumors in brain scans. This is systematic image segmentation, where each pixel in this image is classified as we want to determine the exact location and shape of tumors. Okay, in the head, and typically using CNNs or transformers. Okay, automatically classifying articles,
Automatically classifying news articles.
news
This is natural
articles.
language processing, and more specifically text classification, which can be tackled using recurrent neural networks and CNNs. But transformers work
You
even
can using recurrent neural networks, RNNs and CNNs, conventional neural networks, but transformers work even better. You can see chapter number 16.
better. Automatically flagging offensive comments on discussion forums. This is also text classification, using the same NLP tools.
Yeah,
Summarizing long documents automatically. This is a branch of NLP called text summarization, again using the same tools. Creating a chatbot or a personal assistant. This involves many
the this thing summarization tool is also here. You can see here. This is I am using currently. So this also use natural language processing NLP text summarization. I can summarize the whole chapter. I will first read the chapter number 1 of this book. Then I will summarize it. I will show you how it is done. Okay, this tool how it works, and then chat box. This is AI chat box. You can see what any question related to this document that I am reading. I can ask question, and I will get the answers instantly by this AI chatbot, personal assistant. You can see this involves NLP. This also involves natural language processing components, NLP components, including natural language understanding, NLU, and question answering module. You can see I can ask any question, it will answer. I suppose I ask a simple question: who is the author of this book? Okay, I can ask, and it will answer it by reading all the text. Okay, the author of the
assistant
book.
reply. The author of the book, Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow, is Aurélien Géron.
Aurélien Géron. This is he. Uh, this is the author. Now going to start it.
NLP components, including natural language understanding and question answering modules. Forecasting your company's revenue next year, based on many performance metrics. This is a regression task that may be tackled using any regression model, such as a linear regression or a polynomial regression model, a regression support vector machine, a regression random forest, or an artificial neural network. If you want to take into account sequences of past performance metrics, you may want to use RNNs, CNNs, or transformers. Making your app react to voice commands. This is
So making your app react to voice command. You can see also this.
speech recognition, which requires processing audio samples. Since they are long and complex sequences, they are typically processed using RNNs, CNNs, or transformers. Detecting credit card fraud. This is anomaly detection, which can be tackled using isolation forests, Gaussian mixture models, or autoencoders. Segmenting clients based on their purchases so that you can design a different marketing strategy for each segment. This is clustering, which can be achieved using k-means, DBSCAN, and more.
Emerged, yeah.
Representing a complex, high-dimensional dataset in a clear and insightful diagram, this is data visualization, often involving dimensionality reduction techniques. Recommending a product that a client may be interested in. Based on past purchases, this is a recommender system.
Yeah.
One approach is to feed past purchases to an artificial neural network. and get it to output the most likely next purchase.
Yeah, yeah,
This neural net would typically be trained on past sequences of purchases across all clients. Building an intelligent bot for a game. This is often tackled using reinforcement learning, which is a branch of machine learning that trains agents to pick the actions that will maximize their rewards over time within a given environment. The famous AlphaGo program that beat the world champion at the game of Go was built using RL. This list could go on, but hopefully it gives you a sense of the incredible breadth and complexity of the tasks that machine learning can tackle and the types of techniques that you would use for each task. Types of machine learning systems. There are so many different types of machine learning systems that it is useful to classify them in broad categories based on the following criteria: how they are supervised during training, whether or not they can learn incrementally on the fly, whether they work by
you can see how they are supervised during training. You can see uh, there are five types of supervised, unsupervised, semi-supervised, and self-supervised, and maybe some others. So these type of supervised trainings are there: supervised, unsupervised, semi-supervised, and self-supervised, and some other also. Okay, whether or not they can be learned incrementally on the fly, online versus batch learning. Okay, okay, whether they are working by simply
simply comparing new
comparing
data points to
data
known data
to not
points,
data
or
points.
instead by detecting patterns in the training data and building a predictive model, much like scientists do. These criteria are not exclusive. You can combine them in any way you like. For example, a state-of-the-art spam filter may learn on the fly using a deep neural network model trained using human-provided examples of spam and ham. This makes it an online, model-based, supervised learning system. Let's look at each of these criteria a bit more closely. Training supervision. ML systems can be classified according to the amount and type of supervision they get during training. There are many categories, but we'll discuss the main ones: supervised learning, unsupervised learning, self-supervised learning, semi-supervised learning, and
And
reinforcement learning.
reinforcement.
Supervised learning. In supervised learning, the
So
training
we got to discuss these main ones. There are many categories, but these are the main ones: the supervised, unsupervised, self-supervised, and semi-supervised, and reinforcement learning. Supervised learning, unsupervised learning, and self-supervised learning, and semi-supervised learning, and reinforcement learning. I'm going to study first, starting from supervised learning. So, supervised learning, the training set we feed to the algorithm includes the desired solution called levels. Okay, you can see
set
the
you feed to
levels.
the algorithm includes the desired solutions called labels.
Levels.
Figure 1-5, a labeled training set for spam classification. A typical supervised learning task is classification. The spam filter is a good example of this. It is trained with many example emails along with their class, and it must learn how to classify new emails. Another typical task is to predict a target numeric value, such as the price of a car, given a set of features. This sort of task is called regression. To train the system, you need to give it many examples of cars, including both their features and their targets. Note that some regression models can be used for classification as well, and vice versa. For example, logistic regression is commonly used for classification, as it can. One fun fact: this odd-sounding name is a statistics term introduced by Francis Galton while he was studying the fact that the children of tall people tend to be shorter than their parents. Since the children were shorter, he called this regression to the mean. This name was then applied to the methods he used to analyze correlations between variables. Output a value that corresponds to the probability of belonging to a given class. Figure 1-6. A regression problem. Predictive value given an input feature.
You can see here. Now we are in this is a regression problem. We have to predict a value given an input feature. Some feature is given, and by seeing the input feature, we are using multiple input features and sometimes multiple output values. Okay. The words target and level are generally.
The words target and label are generally treated as synonyms in supervised learning, but target is more common in regression tasks, and label is more common in classification tasks.
So you can see the target is more common in the regression task, and level is more common in classification task. So for different tasks, we are using the same name, the same label name into two different names. Target is for regression task and label for classification task. Okay. Moreover,
Moreover, features are sometimes called predictors or attributes.
attributes. Yeah.
These terms may refer to individual samples or to all samples. Unsupervised learning. In
You can see the example. This car's mileage feature is equal to 15,000. You can so these moral features are sometimes called predators or attributes. You can to all samples. For individual sample, we will call feature. Okay, and for to all samples, we will call the feature. The mileage feature is strongly correlated with price. Okay, you can say that. The car's mileage feature is this, and the mileage feature is strongly correlated with price. So unsupervised learning. Unsupervised learning.
Supervised learning, as you might guess, the training data is unlabeled.
Yeah.
The system tries to learn without a teacher.
ठीक है.
For example, say you have a lot of data about your blog's visitors. You may want to run a clustering algorithm to try to detect groups of similar visitors. At no point do you tell the algorithm which group a visitor belongs to. It finds those connections without your help. For example, it might notice that 40% of your visitors are teenagers who love comic books and generally read your blog after school, while 20% are adults who enjoy sci-fi and who visit during the weekends. If you use a hierarchical clustering algorithm, it may also subdivide each group into smaller groups. This may help you target your post for each group. Figure 1-7, an unlabeled training set for unsupervised learning. Figure 1-8, clustering. Visualization algorithms are also good examples.
You can see here, this is a figure 1-7, unlabeled training set for unsupervised learning. This is totally unlabeled. Nothing is labeled here, but some random sets are given. And it's given to train unsupervised learning. It's not clustering. This is a clustering classification. Everything is classified here, clustered here. The visualization algorithm are also good example.
Of unsupervised learning, you feed them a lot of complex and unlabeled data, and they output a 2D or 3D representation of your data that can easily be plotted.
Yeah.
These algorithms try to preserve as much structure as they can so that you can understand how the data is organized and perhaps identify unsuspected patterns. A related task is dimensionality reduction, in which the goal is to simplify the data without losing too much information. One way to do this is to merge several correlated features into one. For example, a car's mileage may be strongly correlated with its age, so the dimensionality reduction algorithm will merge them into one feature that represents the car's wear and tear. This is called feature extraction. Figure 1-9. Example of a TSNA visualization highlighting semantic clusters.
You can see this is an example of a TSNE supervised. Okay, TSNE visualizations highlighting semantic clusters. There are semantic clusters. So you can see cats, automobile, trucks, frog. These are, I think, these are frog. These are truck, ship, airplane, horse, bird, dog, and deer.
It is often a good idea to try to reduce the number of dimensions in your training data using a dimensionality reduction algorithm before you feed it to another machine learning algorithm. It will run much faster, the data will take up less disk and memory space, and in some cases, it may also perform better. Yet another important unsupervised task is anomaly detection, for example, detecting unusual credit card transactions to prevent fraud, catching manufacturing defects, or automatically removing outliers from a dataset before feeding it to another learning algorithm.
Yeah.
The system is shown mostly normal instances during training, so it learns to recognize them. Then, when it sees a new instance, it can tell whether it looks like a normal one or whether it is likely an anomaly.
Yeah.
A very similar task is novelty detection. It aims to detect new instances that look different from all instances in the training set. This requires having a very clean training set, devoid of any instance that you would like the algorithm to detect. For example, if you have thousands of pictures of dogs, and 1% of these pictures represent chihuahuas, then a novelty detection algorithm should not treat new pictures of chihuahuas as novelties. On the other hand, anomaly detection algorithms may consider these dogs as so rare and so different from other dogs that they would likely classify them as anomalies. Figure 1-10. Anomaly detection. Finally, another common unsupervised task is association rule learning, in which the goal is to dig into large amounts of data and discover interesting relations between attributes. For example, suppose you own a supermarket. Running an association rule on your sales logs may reveal that people who purchase barbecue sauce and potato chips also tend to buy steak. Thus, you may want to place these items close to one another. Semi-supervised learning. Since labeling data is usually time-consuming and costly, you will often have plenty of unlabeled instances and few labeled instances. Some algorithms can deal with data that's partially labeled.
It means there's partially labeled and partially unlabeled. Okay. So this is a semi-supervised learning. Okay.
This is called semi-supervised learning. Figure 1-11. Supervised learning with two classes. The unlabeled examples help classify a new instance into the triangle class rather than the square class, even though it is closer to the labeled squares. Some photo hosting services, such as Google Photos, are good examples of this. Once you upload all your family photos to the service, it automatically recognizes that the same person A shows up in photos 1, 5, and 11, while another person B shows up in photos 2, 5, and 7. This is the unsupervised part of the algorithm. Now all the system needs is for you to tell it who these people are. Just add one label per person, and it is able to name everyone in every photo, which is useful for searching photos.
Yes.
Most semi-supervised learning algorithms are combinations of unsupervised and supervised algorithms. For example, a clustering algorithm may be used to group similar instances together, and then every unlabeled instance can be labeled with the most common label in its cluster. Once the whole dataset is labeled, it is possible to use any supervised learning algorithm. Self-supervised learning. Another approach to machine learning involves actually generating a fully labeled dataset from a fully unlabeled one. Again, once the whole dataset is labeled, any supervised learning algorithm can be used. This approach is called self-supervised learning. For example, if you have a large dataset of unlabeled images, you can randomly mask a small part of each image and then train a model to recover the original image. During training, the masked images are used as the inputs to the model, and the original images are used as the labels. Figure 1-12. Self-supervised learning example, input and target. The resulting model may be quite useful in itself, for example, to repair damaged images or to erase unwanted objects from pictures. But more often than not, a model trained using self-supervised learning is not the final goal. You usually want to tweak and fine-tune the model for a slightly different task, one that you actually care about. For example, suppose that what you really want is to have a pet classification model. Given a picture of any pet, it will tell you what species it belongs to. If you have a large dataset of unlabeled photos of pets, you can start by training an image repairing model using self-supervised learning. Once it's performing well, it should be able to distinguish different pet species. When it repairs an image of a cat whose face is masked, it must know not to add a dog's face. Assuming your model's architecture allows it, it is then possible to tweak the model so that it predicts pet species, instead of repairing images. The final step consists of fine-tuning the model on a labeled dataset. The model already knows what cats, dogs, and other pet species look like. So this step is only needed so the model can learn the mapping between the species it already knows and the labels we expect from it.
Nice.
Transferring knowledge from one task to another is called transfer learning, and it's one of the most important techniques in machine learning today, especially when using deep neural networks. We will discuss this in detail in part second. Some people consider self-supervised learning to be a part of unsupervised learning, since it deals with fully unlabeled datasets. But self-supervised learning uses labels during training, so in that regard it's closer to supervised learning. And the term unsupervised learning is generally used when dealing with tasks like clustering, dimensionality reduction, or anomaly detection, whereas self-supervised learning focuses on the same tasks as supervised learning, mainly classification and regression. In short, it's best to treat self-supervised learning as its own category.
Yeah.
Reinforcement learning. Reinforcement learning is a very different beast. The learning system, called an agent in this context, can observe the environment, select and perform actions, and get rewards in return. It must then learn by itself what is the best strategy, called a policy, to get the most reward over time. A policy defines what action the agent should choose when it is in a given situation.
Yeah.
Figure 1-13. Reinforcement learning.
You can see this, very important. So this is reinforcement learning. First, the agent will observe the actions using policy. This is a select. Okay. And then it perform action, get reward or penalty out. If this in this case penalty because you want fire. Or update policy, learning step. But next time avoid it. Iterate only an optimal policy is found. Okay, you can see this. Okay, going to start the reinforcement learning now. You can see this is the environment where the agent is he's standing here. This is a robot. Now here is fire and here is water. This agent will observe and select action using policy. Okay. Now next it will take action. First by starting I can do. Oh fine, it's recording. So the next it will take action. Either it will go to fire or either it will go to this basket to get reward or penalty. This is penalty minus 50 points. And this is bad. Next time avoid it. Update policy learning step. Now it will go to here. Iterate until an optimal policy is found. Now optimal policy it will get here. So going to start the lecture now.
For example, many robots implement reinforcement learning algorithms to learn how to walk. DeepMind's AlphaGo program is also a good example of reinforcement learning. It made the headlines in May 2017 when it beat Keras, the #1 ranked player in the world at the time, at the game of Go. It learned its winning policy by analyzing millions of games, and then playing many games against itself. Note that learning was turned off during the games against the champion. AlphaGo was just applying the policy it had learned. As you will see in the next section, this is called offline learning.
Offline learning, yeah.
Batch versus online learning. Another criterion used to classify machine learning systems is whether or not the system can learn incrementally from a stream of incoming data. Batch learning. In batch learning, the system is incapable of learning incrementally. It must be trained using all the available data. This will generally take a lot of time and computing resources, so it is typically done offline. First, the system is trained, and then it is launched into production and runs without learning anymore. It just applies what it has learned. This is called offline learning. Unfortunately, a model's performance tends to decay slowly over time, simply because the world continues to evolve while the model remains unchanged. This phenomenon is often called model rot or data drift. The solution is to regularly retrain the model on up-to-date data. How often you need to do that depends on the use case. If the model classifies pictures of cats and dogs, its performance will decay very slowly. But if the model deals with fast-evolving systems, for example making predictions on the financial market, then it is likely to decay quite fast. Even a model trained to classify pictures of cats and dogs may need to be retrained regularly. Not because cats and dogs will mutate overnight, but because cameras keep changing. along with image formats, sharpness, brightness, and size ratios. Moreover, people may love different breeds next year, or they may decide to dress their pets with tiny hats. Who knows? If you want a batch learning system to know about new data, you need to train a new version of the system from scratch on the full dataset, then replace the old model with the new one. Fortunately, the whole process of training, evaluating, and launching a machine learning system can be automated fairly easily, so even a batch learning system can adapt to change. Simply update the data and train a new version of the system from scratch as often as needed. This solution is simple and often works fine, but training using the full set of data can take many hours, so you would typically train a new system only every 24 hours or even just weekly. If your system needs to adapt to rapidly changing data, then you need a more reactive solution. Also, training on the full set of data requires a lot of computing resources. If you have a lot of data and you automate your system to train from scratch every day, it will end up costing you a lot of money. If the amount of data is huge, it may even be impossible to use a batch learning algorithm. Finally, if your system needs to be able to learn autonomously and it has limited resources, then carrying around large amounts of training data and taking up a lot of resources to train for hours every day is a showstopper. A better option in all these cases is to use algorithms that are capable of learning incrementally.
Yeah.
Online learning. In online learning, you train the system incrementally by feeding it data instances sequentially, either individually or in small groups called mini-batches. Each learning step is fast and cheap, so the system can learn about new data on the fly as it arrives. Figure 1-14. Learning, a model is trained and launched into production, and then it keeps learning as new data comes in.
So I'm going to show you this figure. This is an online learning. A model is trained and launched into production, and then it keeps learning as new data comes in. You can see, first we will train the machine learning models using this data, then evaluate, and then launch, and then run and learn on new data on the fly. Okay, this is okay.
Online learning is useful for systems that need to adapt to change extremely rapidly. It is also a good option if you have limited computing resources, for example, if the model is trained on a mobile device. Additionally, online learning algorithms can be used to train models on huge datasets that cannot fit in one machine's main memory. The algorithm loads part of the data, runs a training step on that data, and repeats the process until it has run on all of the data.
Yeah,
Figure
that's cool.
1-15. Using online learning to handle huge datasets.
You can see using online learning to handle huge data sets. You can see this. Lot of data is here, and study the problem. Train online machine learning model. They're using this data, lots of data. Then evaluate, then analyze error, then study the problem. If they again the problem, then train an online machine learning model using the new data, then evaluate, then launch. Okay, this thing you can do.
One important parameter of online learning systems is how fast they should adapt to changing data. This is
Yeah.
called the learning rate. If you set a high learning rate, then your system will rapidly adapt to new data, but it will also tend to quickly forget the old data. Conversely, if you set a low learning rate, the system will have more inertia, that is, it will learn more slowly, but it will also be less sensitive to noise in the new data or to sequences of non-representative data points. Out-of-core learning is usually done offline, so online learning can be a confusing name. Think of it as incremental learning. A big challenge with online learning.
So out of code, learning is usually done offline. Okay, that is not on live system. So online learning name is different. Let's be cautious. It's not so online learning is done online. It may be offline. So usually done offline. So don't be confused about the name. Think of it as incremental learning. This is incremental learning. You can say uh, just learning rate. Okay, fine.
A big challenge with online learning is that if bad data is fed to the system's performance will decline, possibly quickly. If it's a live system, your clients will notice. For example, bad data could come from a bug, or it could come from someone trying to game the system. To reduce this risk, you need to monitor your system closely and promptly switch learning off if you detect a drop in performance. You may also want to monitor the input data and react to abnormal data, for example, using an anomaly detection algorithm. Instance-based versus model-based learning. One more way to categorize machine learning systems is by how they generalize. Most machine learning tasks are about making predictions. This means that given a number of training examples, the system needs to be able to make good predictions for examples it has never seen before. Having a good performance measure on the training data is good, but insufficient. The true goal is to perform well on new instances. There are two main approaches to generalization: instance-based learning and model-based learning. Instance-based learning. Possibly the most trivial form of learning is simply to learn by heart. If you were to create a spam filter this way, it would just flag all emails that are identical to emails that have already been flagged by users. Not the worst solution, but certainly not the best. Instead of just flagging emails that are identical to known spam emails, your spam filter could be programmed to also flag emails that are very similar to known spam emails. This requires a measure of similarity between two emails. A similarity measure between two emails could be to count the number of words they have in common. The system would flag an email as spam if it has many words in common with a known spam email. This is called instance-based learning. The system learns the examples by heart, then generalizes to new cases by using a similarity measure to compare them to the learned examples. For example, in Figure 1-16, the new instance would be classified as a triangle because the majority of the most similar instances belong to that class. Figure 1-16. Instance-based learning, model-based learning in a typical machine learning workflow. Another way to generalize from a set of examples is to build a model of these examples and then use that model to make predictions. This is called model-based learning. Figure 1-17. Model-based learning. For example, suppose you want to know if money makes people happy, so you download the Better Life Index data from the OECD's website and World Bank stats about gross domestic product per capita. Then you join the tables and sort by GDP per capita. Table 1-1 shows an excerpt of what you get. Table 1-1. Does money make people happier? Figure 1-18. Do you see a trend here? There does seem to be a trend here. Although the data is noisy, it looks like life satisfaction goes up more or less linearly as the country's GDP per capita increases. So you decide to model life satisfaction as a linear function of GDP per capita. This step is called model selection. You selected a linear model of life satisfaction with just one attribute, GDP per capita. Equation 1-1. A simple linear model. Life satisfaction equal to plus 6 times GDP per capita. This model has two model parameters, 8 and 8. By tweaking these parameters, you can make your model represent any
You can
linear
see
function.
the theta naught, theta 0 and theta 1, theta naught and theta 1. By sticking this parameter, by tweaking these parameters, you can make your model represent any linear function as shown in figure. This figure 119. A few possible linear model, you can see this theta naught is equal to 4.2 and theta 1 is equal to 0. Theta naught, this is the red line. Theta 1 is 0 and theta naught is 4.2. And this is theta naught is equal to 3. And theta 1 is equal to 8 into 10 to the power minus 5. Theta naught 10, theta 1 minus 9, 10 to the power minus 5. You can see this.
As shown in Figure 1-19. A few possible linear models. Before you can use your models, you need to define the parameter values. How can you know which values will make your model perform best? To answer this question, you need to specify a performance measure. You can either define a utility function that measures how good your model is, or you can define a cost function that measures how bad it is. For linear regression problems, people typically use a cost function that measures the distance between the linear model's predictions and the training examples. The objective is to minimize this distance. This is where the linear regression algorithm comes in. You feed it your training examples, and it finds the parameters that make the linear model fit best to your data. This is called training the model. In our case, the algorithm finds that the optimal parameter values are 0 equal to 3.75 and do1 equal to 6.78 times 10 to 5. Confusingly, the word model can refer to a type of model, to a fully specified model architecture, or to the final trained model ready to be used for predictions. Model selection consists in choosing the type of model and fully specifying its architecture. Training a model means running an algorithm to find the model parameters that will make it best fit the training data, and hopefully make good predictions on new data. Now, the model fits the training data as closely as possible, as you can see in Figure 1-20. Figure 1-20, the linear model that fits the training data best.
Yeah.
You are finally ready to run the model to make predictions. For example, say you want to know how happy Cypriots are, and the OECD data does not have the answer. Fortunately, you can use your model to make a good prediction. You look up Cyprus's GDP per capita, find $37,655, and then apply your model, and find that life satisfaction is likely to be somewhere around 3.75 plus 37, 5 plus 37.55. Ake 1 shows the Python code that loads the inputs x from the labels y, creates a scatterplot for visualization, and then trains a linear model and makes a prediction.
That's cool.
Example 1-1. Training and running a linear model using Scikit-Learn. Import matplotlib.pyplot as plt import numpy as np import pandas as pd from sklearn.linear model. Import linear regression.
Yeah.
Hashtag download and prepare the data root equal to lifesat equal to pd read csv. X equal to lifesat. Values y equal to lifesat. Values hashtag visualize the data lifesat plot. Y equal to life satisfaction plt.axis. plt. Hashtag select a linear model equal to linear regression. Hashtag train the model fit. Hashtag make a prediction for Cyprus xnew equal to. Hashtag Cyprus GDP per capita in 2020 print. Hashtag output. 5. It's okay if you don't.
So this is the program. You can see this example. First, we imported our matplot pyplot library from plot numpy as np. Okay, as np. Okay, pandas as pd. Skylern dot sklearn dot linear model import linear regression. From this module we imported this library. From this library we imported this module linear regression, and then the data root life set x life set values, so life set of float, the kind scatter, grid Jew, x GDP per capita, USD, and y set life satisfaction. We have given these both, and the plot at our axis we have plotted it, and plot dot source is on it. The model linear regression we have done. Modular fit xy. Okay.
Don't understand all the code yet. I will present Scikit-Learn in the following chapters. If you had used an instance-based learning algorithm instead, you would have found that Israel has the closest GDP per capita to that of Cyprus. And since the OECD data tells us that Israelis' life satisfaction is 7.2,
Yeah.
you would have predicted a life satisfaction of 7.2. If you zoom out a bit and look at the two next countries, you will find Lithuania and Slovenia both with a life satisfaction of 5.9. These three values, you get 6.33, which is pretty close to your model-based prediction. This simple algorithm is called k-nearest neighbors regression. Replacing the linear regression model with k-nearest neighbors regression in the previous code is as easy as replacing these lines. From Scikit-Learn.linear model, import linear regression model equal to linear regression. With these two, from Scikit-Learn.neighbors import neighbors regressor model neighbors regressor. If all went well, your model may need to use more attributes, get more, better quality training data, or perhaps select a more powerful model. In summary, you studied the data, you selected a model, you trained it on the training data. Finally, you applied the model to make predictions on new cases, hoping that this model will generalize well. This is what a typical machine learning project looks like. In Chapter 2, you'll experience this firsthand by going through a project end to end. We have covered a lot of ground so far. You now know what machine learning is really about, why it is useful, what some of the most common categories of ML systems are, and what a typical project workflow looks like. Now let's look at what can go wrong in learning and prevent you from making accurate predictions. Main challenges of machine learning. In short, since your main task is to select a model and train it on some data, the two things that can go wrong are bad model and bad data. Let's start with examples of bad data. Insufficient quantity of training data. For a toddler to learn what an apple is, all it takes is for you to point to an apple and say apple. Now the child is able to recognize apples in all sorts of colors and shapes. Genius.
Yes.
Machine learning is not quite there yet. It takes a lot of data for most machine learning algorithms to work properly. Even for very simple problems, you typically need thousands of examples. And for complex problems such as image or speech recognition, you may need millions of examples. The unreasonable effectiveness of data. In a famous paper published in 2001, Microsoft researchers Michelle Banco and Eric Brill showed that very different machine learning algorithms, including fairly simple ones, performed almost identically well on a complex problem of natural language disambiguation once they were given enough data. As the authors put it, these results suggest that we may want to reconsider the trade-off between spending time and money on algorithm development versus spending it on corpus development. The idea that data matters more than algorithms for complex problems was further popularized by Peter Norvig et al. In a paper titled The Unreasonable Effectiveness of Data, published in 2009. It should be noted, however, that small and medium-sized datasets are still very common, and it is not always easy or cheap to get extra training data, so don't abandon algorithms just yet. Figure 1-21. The importance of data versus algorithms. Non-representative training data.
You can see the importance of data versus algorithm. Here the millions of words, and the test accuracy you can see here. The memory bus is like this. This is the memory bus graph. This is window graph. You can see here, and this is Prescriptron, and this is the nav bias. Okay, fine. Non-representative training data.
In order to generalize well, it is crucial that your training data be representative of the new cases you want to generalize to. This is true whether you use instance-based learning or model-based learning. For example, the set of countries you used earlier for training the linear model was not perfectly representative. It did not contain any country with a GDP per capita lower than $23,500 or higher than $23,000. Shows what the data looks like when you add such countries. You get the solid line. While the old model is represented as adding a few missing countries significantly alter the model, but it makes it clear that such a simple linear model is probably never going to work well. It seems that very rich countries are not happier than moderately rich countries. And conversely, some poor countries seem happier than many rich countries.
Yeah.
By using a non-representative training set, you trained a model that is unlikely to make accurate predictions, especially for very poor and very rich countries. Figure 1-22. A more representative training sample. It is crucial to use a training set that is representative of the cases you want to generalize to. This is often harder than it sounds. If the sample is too small, you will have sampling noise. But even very large samples can be non-representative if the sampling method is flawed. This is called sampling bias.
Okay.
Examples.
This is called sampling bias. This is very important. You can see the more representative training sample here. This is two lines. This South Africa is in Colombia, Brazil, Mexico, Chad is Lazarus in upper. And Norway, Switzerland is also higher than that line. Ireland and Luxembourg. Hmm. This yeah. Sampling noise, but even very large samples can non-representative if the sampling data is flawed. This is it's called sampling bias. Okay.
Of sampling bias. Perhaps the most famous example of sampling bias happened during the US presidential election in 1936, which pitted Landon against Roosevelt. The Literary Digest conducted a very large poll. It got 2.4 million answers and predicted with high confidence that Landon would get 57% of the votes. Instead, Roosevelt won with 62% of the votes. The flaw was in the Literary Digest's sampling method. First, to obtain the addresses to send the polls to, the Literary Digest used telephone directories, lists of magazine subscribers, club membership lists, and the like. It tended to favor wealthier people, who were more likely to vote Republican. Second, less than 25% of the people who were polled answered. Again, this introduced a sampling bias by potentially ruling out people who didn't care much about politics, people who didn't like the Literary Digest, and other key groups. This is a special type of sampling bias called non-response bias. Here's another example. Say you want to build a system to recognize funk music videos. One way to build your training set is to search for funk music on YouTube and use the resulting videos. But this assumes that YouTube's search engine returns a set of videos that are representative of all the funk music videos on YouTube. In reality, the search results are likely to be biased toward popular artists. And if you live in Brazil, you will get a lot of funk karaoke videos, which sound nothing like James Brown. On the other hand, how else can you get a large training set? Poor quality data. Obviously, if your training data is full of errors, outliers, and noise, it will make it harder for the system to detect the underlying patterns, so your system is less likely to perform well.
Yeah.
It is often well worth the effort to spend time cleaning up your training data. The truth is, most data scientists spend a significant part of their time doing just that. The following are a couple examples of when you'd want to clean up training data. If some instances are clearly outliers, it may help to simply discard them or try to fix the errors manually. If some instances are missing a few features, you must decide whether you want to ignore this attribute altogether, ignore these instances, fill in the missing values, or train one model with the feature and one model without it. Irrelevant features. As the saying goes, garbage in, garbage out. Your system will only be capable of learning if the training data contains enough relevant features and not too many irrelevant ones. A critical part of the success of a machine learning project is coming up with a good set of features to train on. This process, called feature engineering, involves the following steps: feature selection, feature extraction, creating new features by gathering new data. Now that we have looked at many examples,
So that's good. Feature selection means selecting the most useful feature to train on among existing features. Okay. Select most useful features to train on among existing features, and feature extraction, combining existing features to produce a more useful one, as we saw earlier. This is feature extraction, combining existing features to produce a more useful one, as we saw earlier. Dimensionality reduction algorithms can help. Now creating new feature by gathering new data. This is also good. Now that we have looked so many example of bad data,
bad
let's
data, let's look at a couple examples of bad algorithms.
yeah.
Overfitting the training data. Say you are visiting a foreign country, and the taxi driver rips you off. You might be tempted to say that all taxi drivers in that country are thieves. Overgeneralizing is something that we humans do all too often. And unfortunately, machines can fall into the same trap if we are not careful.
Yeah.
In machine learning, this is called overfitting. It means that the model performs well on the training data, but it does not generalize well. Figure 1-23 shows an example of a high-degree polynomial life satisfaction model that strongly overfits the training data. Even though it performs much better on the training data than the simple linear model, would you really trust its predictions? Figure 1-23. Overfitting the training data. Complex models such as deep neural networks can detect subtle patterns in the data. But if the training set is noisy, or if it is too small, which introduces sampling noise, then the model is likely to detect patterns in the noise itself. Obviously, these patterns will not generalize to new instances. For example, say you feed your life satisfaction model many more attributes, including uninformative ones such as the country's name. In that case, a complex model may detect patterns like the fact that all countries in the training data with a W in their name have a life satisfaction greater than 7. New Zealand, Norway, Sweden, and Switzerland. How confident are you that the W satisfaction rule generalizes to Rwanda or Zimbabwe? Obviously, this pattern occurred in the training data by pure chance. But the model has no way to tell whether a pattern is real or simply the result of noise in the data. Overfitting happens when the model is too complex relative to the amount and noisiness of the training data. Here are possible solutions. Simplify the model by selecting one with fewer parameters, by reducing the number of attributes in the training data.
You can select this few parameters. You can select a linear model rather than high degree polynomial model, or by reducing the number of attributes in the training data, or by constraining the model. Okay.
Or by constraining the model. Gather more training data. Reduce the noise in the training data. Constraining a model to make it simpler and reduce the risk of overfitting is called regularization. For example, the linear model we defined earlier has two parameters, 8 and 8. This gives the learning algorithm 2 degrees of freedom to adapt the model to the training data. It can tweak both the height and the slope of the line. If we force 0, 0, the algorithm would have only 1 degree of freedom and would have a much harder time fitting the data properly. All it could do is move the line up or down to get as close as possible to the training instances. So it would end up around the mean. A very simple model indeed. If we allow the algorithm to modify 8, but we force it to keep it small, then the learning algorithm will effectively have somewhere in between 1 and 2 degrees of freedom. It will produce a model that's simpler than 1 with 2 degrees of freedom, but more complex than 1 with just 1. You want to find the right balance between fitting the training data perfectly and keeping the model simple enough to ensure that it will generalize well. Figure 1-24 shows 3 models. The dotted line represents the original model that was trained on the countries represented as circles. The solid line is our second model trained with all countries, and the dashed line is a model trained with the same data as the first model, but with a regularization constraint. You can see that regularization forced the model to have a smaller slope. This model does not fit the training data as well as the first model, but it actually generalizes better to new examples that it did not see during training. Figure 1-24. Regularization reduces the risk of overfitting. The amount of regularization to apply during learning can be controlled by a hyperparameter. A hyperparameter is a parameter of a learning algorithm. As such, it is not affected by the learning algorithm itself. It must be set prior to training and remains constant during training. If you set the regularization hyperparameter to a very large value, you will get an almost flat model. The learning algorithm will almost certainly not overfit the training data, but it will be less likely to find a good solution. Tuning hyperparameters is an important part of building a machine learning system. Underfitting the training data. As you might guess, underfitting is the opposite of overfitting. It occurs when your model is too simple to learn the underlying structure of the data. For example, a linear model of life satisfaction is prone to underfit. Reality is just more complex than the model, so its predictions are bound to be inaccurate, even on the training examples.
Yeah, sure.
Here are the main options for fixing this problem. Select a more powerful model with more parameters. Feed better features to the learning algorithm. Reduce the constraints on the model. Stepping back. By now you know a lot about machine learning. However, we went through so many concepts that you may be feeling a little lost, so let's step back and look at the big picture. Machine learning is about making machines get better at some task by learning from data, instead of having to explicitly code rules. There are many different types of ML systems, supervised or not, batch or online, instance-based or model-based.
Yeah.
In an ML project, you gather data in a training set, and you feed the training set to a learning algorithm. If the algorithm is model-based, it tunes some parameters to fit the model to the training set, and then hopefully it will be able to make good predictions on new cases as well.
Yeah.
If the algorithm is instance-based, it just learns the examples by heart and generalizes to new instances by using a similarity measure to compare them to the learned instances.
Yeah.
The system will not perform well if your training set is too small, or if the data is not representative, is noisy, or is polluted with irrelevant features. Lastly, your model needs to be neither too simple nor too complex. There's just one last important topic to cover. Once you have trained a model, you don't want to just hope it generalizes to new cases. You want to evaluate it and fine-tune it if necessary. Let's see how to do that. Testing and validating.
That's cool.
The only way to know how well a model will generalize to new cases is to actually try it out on new cases. One way to do that is to put your model in production and monitor how well it performs. This works well, but if your model is horribly bad, your users will complain. Not the best idea. A better option is to split your data into two sets, the training set and the test set. As these names imply, you train your model using the training set, and you test it using the test set.
Yeah.
The error rate on new cases is called the generalization error, and by evaluating your model on the test set, you get an estimate of this error. This value tells you how well your model will perform on instances it has never seen before. If the training error is low but the generalization error is high, it means that your model is overfitting the training data. It is common to use 80% of the data for training and hold out % for testing. However, this depends on the size of the dataset. If it contains 10 million instances, then holding out 1% means your test set will contain 100,000 instances, probably more than enough to get a good estimate of the generalization error. Hyperparameter tuning and model selection. Evaluating a model is simple enough, just use a test set. But suppose you are hesitating between two types of models. How can you decide between them? One option is to train both and compare how well they generalize using the test set. Now suppose that the linear model generalizes better, but you want to apply some regularization to avoid overfitting. The question is, how do you choose the value of the regularization hyperparameter? One option is to train 100 different models using 100 different values for this hyperparameter. Suppose you find the best hyperparameter value that produces a model with the lowest generalization error, say, just 5% error. You launch this model into production, but unfortunately it does not perform as well as expected and produces 15% errors. What just happened? The problem is that you measured the generalization error multiple times on the test set, and you adapted the model and hyperparameters to produce the best model for that particular set. This means the model is unlikely to perform as well on new data. A common solution to this problem is called holdout validation. You simply hold out part of the training set to evaluate several candidate models and select the best one. The new held out set is called the validation set. More specifically, you train multiple models with various hyperparameters on the reduced training set, and you select the model that performs best on the validation set. After this holdout validation process, you train the best model on the full training set, and this gives you the final model. Lastly, you evaluate this final model on the test set to get an estimate of the generalization error. Figure 1-25. Model selection using holdout validation.
So you can see this figure, model selection using holdout validation. You can see this, there is a training set and development set and test set. So in the training set, we first train multiple models, different kind of models, machine learning models you train. Okay. Then evaluate each models. Okay. And you can't go from evaluating model to again training. Just training set is only train multiple models and then evaluate models. Evaluate models is in development set and then retrain the best model, which is the best model from of this, and then evaluate the final model. And this is the test set. Okay, this thing is done during the holdout validation, model selection using holdout validation. Okay, so this solution is
This solution usually works quite well. However, if the validation set is too small, then the model evaluations will be imprecise. You may end up selecting a suboptimal model by mistake. Conversely, if the validation set is too large, then the remaining training set will be much smaller than the full training set. Why is this bad? Well, since the final model will be trained on the full training set, it is not ideal to compare candidate models trained on a much smaller training set. It would be like selecting the fastest sprinter to participate in a marathon.
Yeah.
One way to solve this problem is to perform repeated cross-validation, using many small validation sets. Each model is evaluated once per validation set after it is trained on the rest of the data. By averaging out all the evaluations of a model, you get a much more accurate measure of its performance. There is a drawback, however. The training time is multiplied by the number of validation sets. Data mismatch. In some cases, it's easy to get a large amount of data for training, but this data probably won't be perfectly representative of the data that will be used in production. For example, suppose you want to create a mobile app to take pictures of flowers and automatically determine their species.
That's cool.
You can easily download millions of pictures of flowers on the web, but they won't be perfectly representative of the pictures that will actually be taken using the app on a mobile device. Perhaps you only have 1,000 representative pictures. In this case, the most important rule to remember is that both the validation set and the test set must be as representative as possible of the data you expect to use in production. So they should be composed exclusively of representative pictures. You can shuffle them and put half in the validation set and half in the test set. After training your model on the web pictures, if you observe that the performance of the model on the validation set is disappointing, you will not know whether this is because your model has overfit the training set, or whether this is just due to the mismatch between the web pictures and the mobile app pictures. One solution is to hold out some of the training pictures in yet another set, that Andrew Ng dubbed the train dev set. After the model is trained, you can evaluate it on the train dev set. If the model performs poorly, then it must have overfit the training set, so you should try to simplify or regularize the model, get more training data, and clean up the training data. But if it performs well on the train dev set, then you can evaluate the model on the dev set. If it performs poorly, then the problem must be coming from the data mismatch. You can try to tackle this problem by pre-processing the web images to make them look more like the pictures that will be taken by the mobile app, and then retraining the model. Once you have a model that performs well on both the train dev set and the dev set, you can evaluate it one last time on the test set to know how well it is likely to perform in production. Figure 1-26. When real data is scarce, you may use similar abundant data for training and hold out some of it in a train dev set to evaluate overfitting. The real data is then used to evaluate data mismatch and to evaluate the final model's performance. No free lunch theorem. A model is a simplified representation of the data. The simplifications are meant to discard the superfluous details that are unlikely to generalize to new instances. When you select a particular type of model, you are implicitly making assumptions about the data. For example, if you choose a linear model, you are implicitly assuming that the data is fundamentally linear, and that the distance between the instances in the straight line is just noise, which can safely be ignored. In a famous 1996 paper, David Wolpert demonstrated that if you make absolutely no assumption about the data, then there is no reason to prefer one model over any other. This is called the no free lunch theorem. For some datasets, the best model is a linear model,
Yeah.
while for other datasets, it is a neural network.
Yeah.
There is no model that is a priori guaranteed to work better. The only way to know for sure which model is best is to evaluate them all. Since this is not possible, in practice you make some reasonable assumptions about the data and evaluate only a few reasonable models. For example, for simple tasks you may evaluate linear models with various levels of regularization, and for a complex problem you may evaluate various neural networks. Exercises. In this chapter we have covered some of the most important concepts in machine learning. In the next chapters we will dive deeper and write more code. But before we do, make sure you can answer the following questions.
So, going to answer each question. Before answering the question, what I can do, I just summarize this lesson once more, okay? Understanding machine learning foundations. Okay, so selecting this current chapter, I can select chapter. Okay, objective and approach, fundamental machine learning. Okay, going to this chapter, chapter number 1. Okay, continue. And why 15 chat is selected? I'm selected only. Yeah, I think so. I think so. Part 1, chapter number 1. Okay, fine. This chapter is selected. Now, making bullet points, deep dive it. Okay, create summary. Okay, creating summary. Okay, going to listen this.
The machine learning landscape. Fundamentals and definitions. Defining machine learning at its core. Machine learning is the science of programming computers to learn from
Starting from
the
this.
machine
Okay.
learning landscape. Fundamentals and definitions. Defining machine learning at its core. Machine learning is the science of programming computers to learn from data without being explicitly coded for every scenario. As articulated by Arthur Samuel in 1959, it enables systems to gain intelligence autonomously, while Tom Mitchell's 1997 definition emphasizes that a program learns if its performance on a specific task improves through experience as measured by a performance metric. The rationale for adoption: traditional programming requires developers to manually author complex, brittle rules that are difficult to maintain in dynamic environments. Machine learning thrives by automatically detecting patterns within data, allowing for shorter, more maintainable code that adapts gracefully to changing trends, such as shifting spam email patterns or evolving user behavior. Problem-solving capabilities. Machine learning is uniquely suited for tasks where traditional algorithmic approaches fail or are too complex to define. It excels at speech recognition, predictive analytics for revenue, anomaly detection for fraud, and data mining, where the objective is to extract hidden, actionable insights from massive datasets.
That's cool.
Categorizing learning systems. Training supervision types. Systems are categorized by the nature of their feedback. Supervised learning utilizes labeled data for tasks like classification or regression. Unsupervised learning deals with unlabeled data, facilitating clustering, dimensionality reduction, and association rule learning. Semi-supervised learning leverages small amounts of labeled data alongside large volumes of unlabeled information, while self-supervised learning generates its own labels through techniques like image masking.
Yeah.
Finally, reinforcement learning involves an agent learning through trial and error within an environment to maximize cumulative rewards.
Yeah.
Learning mechanics. Batch learning requires training the system on the full dataset, which can be computationally intensive but stable.
That's several.
Online learning facilitates incremental training via mini-batches, allowing systems to adapt rapidly to streaming data. Generalization strategies. Instance-based learning relies on comparing new data points to memorized examples using similarity measures. Model-based learning involves building a mathematical representation, a model, from the training data, tuning internal parameters to minimize a cost function and facilitate accurate future predictions.
Yeah.
Operational challenges. Data quality and quantity. The garbage in, garbage out principle dominates machine learning. Insufficient data often hampers performance, as complex models require large training sets. Furthermore, sampling bias and poor quality, noisy or missing data can severely distort a model's ability to learn actual underlying patterns. Feature engineering. A successful project relies on identifying relevant attributes. Feature selection removes unnecessary noise, while feature extraction combines dimensions to improve predictive power. Creating new informed features is often the most critical differentiator between average and high-performing models. Model pitfalls. Overfitting occurs when a model is overly complex and captures random noise, failing to generalize to new instances. Regularization, the process of adding constraints to the model, is essential to maintain simplicity. Conversely, underfitting happens when a model is too simple to capture the complexity of the data, requiring more powerful algorithms or more robust feature sets.
Nice.
Validation and best practices. Evaluation frameworks. Effective evaluation requires splitting data into training and test sets. To avoid tuning models specifically for test data, practitioners utilize a validation set. Cross-validation provides a more statistically sound performance estimate by rotating multiple validation sets, though it increases computational costs. Managing data mismatch. When the training data differs from production data, a trained dev set helps diagnose whether poor performance stems from overfitting or the inherent mismatch between environments. By isolating these variables, data scientists can determine whether to regularize the model or invest in pre-processing to bridge the domain gap. The no free lunch theorem. As demonstrated by David Wolpert, no single algorithm is guaranteed to outperform others on all datasets. Because every model makes different assumptions, there is no best model a priori. Success requires evaluating multiple promising architectures based on reasonable assumptions about the specific domain. Project workflow overview. Structured development. A typical machine learning project follows a rigorous life cycle, defining the objective, gathering raw data, performing exploratory data analysis, cleaning and preparing the data, selecting and training candidate models, fine-tuning hyperparameters, and eventually deploying and monitoring the system. Iterative improvement, machine learning is rarely a linear process. It involves constant cycles of training, testing, and refining. The goal is to move from a simplified model to a complex, well-regularized solution that performs consistently on unseen data. Practical application, moving from theory to practice, involves experimenting with real-world datasets from repositories like Kaggle or OpenML. By following these established workflows, from initial insight gathering to final production monitoring, data scientists can build systems that reliably deliver value in fluctuating, real-world environments. In summary, this overview highlights that machine learning is a multidisciplinary science, balancing data quality, model selection, and iterative validation. By understanding the distinctions between supervised and unsupervised methodologies, recognizing the risks of overfitting and underfitting, and strictly adhering to validation protocols, practitioners can navigate the complexities of data-driven problem solving to create adaptive and effective systems.
Nice summary, nice summary. So going to answer each question, starting from this question, okay? I will ask it, chat with this, okay? Till 8 question, I will ask all the questions. Okay. I think no.
Assistant reply. Let's go through each question step by step. Machine. Assistant reply. Let's go through each question step by step. Machine.
So read here from here. I think some issue is there. What I can do? Machine learning is a field of. How would you define machine learning?
1. How would you define machine learning?
So machine learning is a field of artificial intelligence (AI). It's a enable system to learn from data, identify patterns, okay, and make decisions with minimal human intervention. There's very less human intervention. Mostly the machine do its work, okay, and it's identify patterns and make decision with minimal human intervention, and it involves algorithms, different kind of algorithms, machine learning algorithm that improve over time as they process more data. Okay, this is the answer of the first question. How you define machine learning? It's a field of AI that enables systems to learn from data and identify patterns and make decisions with minimal human intervention. And it involves algorithms that improve over time as they process more and more data. That's the simple definition. Can you name 4 types of applications which where it's science? So 4 types of applications where human machines science, where machine learning science include fraud detection, recommendation system, I already told, and medical diagnosis and autonomous vehicles, e-vehicle. Okay, autonomous vehicles. What is labeled training set? A labeled training set is a data set where each input example is paired with correct output. Yeah, so the model learns to map inputs to the correct outputs during training. So this is the label training set. A label training set is a data set where each input example is paired with correct output. So the model learns to map inputs to the correct output during training. Okay. Now, can you name 4 common unsupervised tasks? The two most, not four. What are 2 most common supervised tasks? So two most common supervised tasks are classification and regression. Classification involves predicting categories, while regression involves predicting continuous values. Okay, classify categories different ways predict, and while regression involves predicting continuous values. Okay, now the 4 common unsupervised tasks include clustering, anomaly detection, dimensionality, reduction, and association rule learning. Okay. This is the for common unsupervised tasks: clustering, anomaly detection, dimensionality reduction, and association rule learning. What type of algorithm would you use to allow a robot to walk in various unknown terrains? So, for a robot to walk in various unknown terrains, a reinforcement learning algorithm would likely be used, where robot learns through trial and error by interacting with environment. Okay. And again, next question: what type of algorithm would you use to segment your customers into multiple groups? To segment customers into multiple groups, you would use a clustering algorithm, okay, which is a common unsupervised learning technique. Okay. Would you frame the problem of spam detection as supervised learning problem or unsupervised learning problem? Spam detection would be framed as a supervised learning problem since the model is trained on labeled data, identifying emails as either spam or not spam. Okay, these are the answer of this question. Next, what is an online? Uh, now, doing the next questions. Solution of this exercise are available at the end of the at the okay fine end of the chapter. So you can see 1 minute. I will read all the questions now. Starting from here.
2. 9.
Okay, fine. Fine. Starting the
Assistant
question.
reply. Let's break down each of these questions. An online learning system is a type of system that processes data in a
What is an online learning system? This is the answer.
sequential manner,
So
updating
an online learning system is a type of system that processes data into sequential manner, updating its model incrementally as new data arrives, rather than returning from scratch. This is an online learning system. The online learning system is a type of system that processes data in a sequential manner, updating its model incrementally as new data arrives rather than retraining from scratch. That's very important. An online learning system is a type of system that processes data in sequential manner, updating its model incrementally, not from scratch. Incrementally as new data arrives rather than retraining from scratch. That's the definition of online learning system. What is out of code learning? Out of code learning refers to algorithm that can handle data sets they don't fit into memory by processing data into chunks or by streaming the data. This is out of code learning. Out of code learning refers to algorithms that can handle data sets that don't fit into memory by processing data into chunks or by streaming the data. Now, what type of algorithm relies on similarity measures to make prediction? So, an algorithm that relies on similarities measure to make prediction is typically k nearest neighbors, KNN in short form. Algorithm k nearest neighbors, KNN algorithm is the algorithm that relies on similarity measures to make prediction. Okay. So, next question is what is difference between a model parameter and model hyperparameter? So, model parameters are learned from the data during training, while model hyperparameters are set before training. So model parameters are learned from data during training, while data hyperparameters are set before training. These are different. Okay, and control aspects of the learning process, such as learning rate or the number of hidden layers. This is hyperparameters. Are learned from data during training, and while data hyperparameters are set before training, and control aspect of the learning process, such as learning rate or a number of hidden layers. Okay, this is the hyperparameter or parameters. Okay, model-based learning. What do model-based learning search for? Model-based algorithms search for, and what is the most common strategy they use to succeed? How do they make prediction? So this is the question number 13. So model-based algorithms searches for a best fit model to represent the data. The most commonly strategy is to minimize a defined loss function. They make prediction based on patterns found in the data model. Okay, and can you name four of the main challenges in machine learning? So, four main challenges in machine learning include overfitting, underfitting, data scarcity, and bias in the data. These are four main challenges in machine learning: include overfitting, underfitting, data scarcity, and bias in the data. So, This is the 4 main challenges. Yeah, nice. And if your model performs great on the training data, but generalize this poorly to new instances, what is happening? Can you name 3 possible solutions? If your model performs great on the training data, but generalize poorly to new data, it's likely overfitting. Okay, it's likely overfitting. Okay. 3 possible solutions include using regularization, gathering more data, and employing cross-validation. This is the 3 possible solutions. The first is regularization, make it regular, gather more data, more and more data, and employing cross-validation, employ cross-validation. 3 possible solutions are this. Now, what is a test set? Why would you want to use it? The test set is a portion of the data that has back from training and used to evaluate the model's performance, ensuring it generalizes well to unseen data. So this is the test set. The test set is proportion of the data that helps back from training and used to evaluate the model's performance, ensuring it generalizes well to unseen data. Okay, the purpose, what is the purpose of validation set? The purpose of validation set is tune the model hyperparameter, tune the model's hyperparameters and prevent overfitting uh, by providing a separate data set to validate the model's performance during training. This is very important. Okay, so this is very important. The purpose of validation set is to tune the model's hyperparameters and prevent overfitting by providing a separate data set to validate the model's performance during training. So, what is the trend dev set? When do you need it and how do you use it? So, a trend dev set, training and development set is used when you need to tune hyperparameters and make model adjustment. It's separate from test set and helps make sure that the model generalize well. You train on training set and validate on the development set. Is separate from the test set and helps make sure that model generalize well. You train on the training set and validate on the development set. Now, what can go wrong if you tune hyperparameters using the test set? If you tune hyperparameters using the test set, you risk outfitting to the test data. Okay, so we test the hyperparameters using the dev set, development set. Okay, the training and development set, tune hyperparameters, make model adjustment is separate from the test set and helps make sure the model analyze well. Okay, and you train on the training set and validate on the development set. Okay, if you tune hyperparameters you're using the test set, you risk outfitting to the test data, which means your evaluation will not reflect true performance of on unseen data. This can lead to overly optimist performance estimates. Okay, this is the answer of this question, and you can also check the solutions of this exercise on this chapter's notebook. And the end of this chapter's notebook, at you can check this note. Okay, I think at the last it is given, no? 66, page number 66. This is, I think, here is given sets. I think this is the Q sets appendix special data structure about all things. This you can go upside. Okay, it's okay. I will check out. Okay, fine. Don't worry about. That's nice. So I will start the second chapter now. Second chapter, end-to-end machine learning project. Before starting,
End to end.
what I can do, I can make a podcast of the chapter number 1 and listen it first, and then make some questions and then answer it by myself without using the AI chat. So I will do that thing. Okay, make 20 questions, select chapters, and select this chapter number 1. Okay, part 1, and I will make the okay, fine. What happened? I think all the questions will be made from this one. So don't select this one, only select this one. Okay, fine. Continue. And you can generate quiz. Okay, I will do that after some time, but I will make postcard. Thoughtful talk and language will be, let's try Hindi. Okay. Uh, if it's work, then it's good. Otherwise, I will change into English. Okay. Now it's create. Now it's creating in Hindi. It will take time. I think so. So around 1 minute it will take. So I will pause it. So hello friend, you can see.
तो मान लीजिए एक स्पैम
So you can see the Hindi podcast here on machine
मशीन
learning.
लर्निंग अब केवल विज्ञान कथा नहीं रह गई है, बल्कि ये हमारे दैनिक जीवन का एक अभिन्न अंग बन गई है। ये एक स्पैम फिल्टर जैसे छोटे उदाहरणों से लेकर सेल्फ ड्राइविंग कारों जैसी जटिल प्रणालियों तक फैला हुआ है।
Nice.
लेकिन क्या वास्तव में एक मशीन के लिए सीखने का मतलब है?
बिल्कुल। मशीन लर्निंग, जैसा कि ऑरेलियन गेरॉन अपनी किताब हैंड्स ऑन मशीन लर्निंग विद साइकिट-लर्न, केरास और टेंसरफ्लो में बताते हैं, कंप्यूटरों को डेटा से सीखने के लिए प्रोग्राम करने की कला और विज्ञान है। ये आर्थर सैमुअल की 1959 की परिभाषा से आगे बढ़ता है, जो कहते हैं कि ये कंप्यूटरों को स्पष्ट रूप से प्रोग्राम किए बिना सीखने की क्षमता देता है।
Nice.
और टॉम मिचेल ने 1997 में इसे टास्क टी पर अनुभव ई से सीखे गए कंप्यूटर प्रोग्राम की परफॉर्मेंस पी के रूप में परिभाषित किया, जो अनुभव से बेहतर होती है।
तो मान लीजिए एक स्पैम फिल्टर का उदाहरण है। ये ईमेल के उदाहरणों से सीखता है, जिन्हें उपयोगकर्ता स्पैम या हैम के रूप में फ्लैग करते हैं। सीखने के लिए उपयोग किए जाने वाले उदाहरणों को ट्रेनिंग सेट कहा जाता है। प्रत्येक उदाहरण एक ट्रेनिंग इंस्टेंस या सैंपल होता है, और जो हिस्सा सीखता है और भविष्यवाणी करता है वह मॉडल कहलाता है।
ये पारंपरिक प्रोग्रामिंग की तुलना में बहुत अलग है। पारंपरिक तरीके से स्पैम फिल्टर बनाने में आपको लंबे और जटिल नियम लिखने होंगे, जैसे फॉर यू, क्रेडिट कार्ड जैसे शब्दों को पहचानना।
No.
लेकिन अगर स्पैमर फॉर यू की जगह फॉर यू लिखना शुरू कर दे, तो आपको नए नियम बनाने होंगे। मशीन लर्निंग में सिस्टम स्वचालित रूप से पैटर्न सीखता है और नए बदलावों के अनुसार खुद को ढाल लेता है। ये नियमों की लंबी सूची के बजाय अधिक गतिशील और कुशल होता है।
तो मशीन लर्निंग उन समस्याओं के लिए भी शानदार है जो पारंपरिक तरीकों से बहुत जटिल है, जैसे स्पीच रिकग्निशन, और ये हमें खुद डेटा से सीखने में मदद करता है, छिपे हुए पैटर्न को उजागर करता है। इसे कहते हैं डेटा माइनिंग।
No.
हाँ, मशीन लर्निंग के उपयोग के कई कारण हैं। जिन समस्याओं में बहुत अधिक फाइन ट्यूनिंग या नियमों की लंबी सूचियों की आवश्यकता होती है, वहाँ ये कोड को सरल बना सकता है। जिन जटिल समस्याओं का कोई पारंपरिक समाधान नहीं है, वहाँ भी मशीन लर्निंग एक रास्ता खोज सकता है।
I think some server issues there. Okay, go back. Okay, open it. Open the podcast. Machine learning fundamental. Nice episode. That's all really good. But I think I should continue in English because most of the audience don't know. Many audience don't know Hindi. So continuing this in English.
Machine learning, once confined to sci-fi, is now performing tasks like ranking your web searches and recommending videos. But what exactly qualifies as learning for a computer? And how has it become so fundamental to our high-tech products today?
That's a great starting point, Elliot. Aurélien Géron, in his book Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow, delves into this. He references Arthur Samuel's 1959 definition, stating, "Machine learning is the field of study that gives computers the ability to learn without being explicitly programmed." More technically, Tom Mitchell in 1997 defined it as a computer program learning from experience, E, with respect to some task, T, and performance measure, P, where its performance on T improves with E.
So it's not just about giving a computer more data, like downloading all of Wikipedia. It's about getting better at a specific task through experience. Can you give us a tangible example? Maybe something we all encounter daily?
Nice.
Absolutely. Think about spam filters. Traditionally, you'd write a long, complex set of rules to catch spam, constantly updating it as spammers evolve their tactics. It's a never-ending maintenance nightmare. With machine learning, you train the filter with examples of spam and non-spam emails. The system then automatically learns the patterns, like specific words or phrases. If spammers switch from "for you" to "for you," the ML filter adapts without direct intervention, learning to flag the new patterns from user feedback.
That's impressive, the adaptability factor. Beyond just solving maintenance issues, what other kinds of problems does machine learning really shine at?
Machine learning is excellent for problems too complex for traditional programming, or those with no known algorithms. Speech recognition is a prime example. Trying to hard code rules for thousands of words across millions of different voices in noisy environments is impossible. ML algorithms learn from vast examples. It's also great for fluctuating environments where data changes rapidly, allowing systems to be continually retrained. And crucially, it helps humans learn by revealing hidden patterns in large data sets, a process we call data mining.
So it's not just automating tasks, but also providing insights. Géron lists a wide array of applications. Can you highlight a few diverse ones and mention the techniques involved?
Certainly, image classification, like automatically classifying products on a production line, uses convolutional neural networks, or CNNs. Detecting tumors in brain scans is semantic image segmentation, also typically using CNNs. For natural language processing tasks, such as classifying news articles or flagging offensive comments, we see recurrent neural networks, or RNNs, and increasingly, transformers. Even something like forecasting next year's revenue is a regression task, handled by models like linear or polynomial regression, support vector machines, or artificial neural networks. And for building intelligent game bots, reinforcement learning is key, as exemplified by DeepMind's AlphaGo beating Go champions.
That's quite a spectrum. Now, Géron categorizes machine learning systems based on several criteria. Let's start with how they're supervised during training. What are the main types there?
The primary types are supervised, unsupervised, semi-supervised, and reinforcement learning. In supervised learning, the training data includes the desired solutions, called labels. Classification, like the spam filter, and regression, like predicting car prices, are typical supervised tasks. In contrast, unsupervised learning deals with unlabeled data. The system learns on its own, for example, a clustering algorithm grouping customers by buying habits. Other unsupervised tasks include data visualization, dimensionality reduction, anomaly detection, and association rule learning.
So, supervised has a teacher, unsupervised doesn't. What about semi-supervised learning?
Semi-supervised learning is a blend. It's for when you have lots of unlabeled data, but only a few labeled instances. Think of Google Photos. It clusters images of the same person automatically. That's unsupervised. Then you just label one or two photos for each person, and the system can name everyone in all their photos. Most semi-supervised algorithms combine unsupervised and supervised techniques. Then there's self-supervised learning, where you generate a fully labeled data set from an unlabeled one, for instance, by masking parts of images and training a model to recover the original. This is crucial for transfer learning in deep neural networks.
And finally, reinforcement learning.
Reinforcement learning is very different. An agent observes an environment, selects actions, and gets rewards or penalties. It then learns the best strategy or policy to maximize cumulative rewards over time. AlphaGo, the Go-playing AI, is a perfect example. It learned by analyzing millions of games and then playing against itself.
Yeah.
Moving on to another classification criterion, how systems learn incrementally. We have batch learning versus online learning. Can you differentiate these?
Batch learning means the system can't learn incrementally. It's trained offline using all available data. Once trained, it's deployed and applies what it's learned without further adaptation. This is efficient, but suffers from model rot as real-world data changes. The solution is regular retraining from scratch on updated data sets. Online learning, however, trains the system incrementally by feeding it data instances sequentially, often in small groups called mini batches.
This allows rapid adaptation to new data, and it's also suitable for huge data sets that can't fit into memory, known as out-of-core learning.
So online learning is more dynamic. What are the main challenges or risks associated with online learning?
The main challenge is that if bad data is fed to an online system, its performance can degrade quickly. This could be due to a bug or someone trying to game the system. Robust monitoring is essential, and if a performance drop is detected, learning might need to be temporarily switched off or the system reverted to a previous state. Also, setting the learning rate is crucial. Too high, and it adapts quickly, but forgets old data easily. Too low, and it learns slowly, but is less sensitive to noise.
Nice.
That's a delicate balance. Let's touch on the third criterion, instance-based versus model-based learning. What's the core distinction here?
This relates to how systems generalize to new unseen cases. Instance-based learning simply learns all examples by heart. When presented with a new case, it generalizes by comparing it to the learned examples using a similarity measure. For instance, a spam filter might flag an email if it's very similar to a known spam email. Model-based learning, however, builds a predictive model from the training examples. It detects patterns and relationships much like scientists form hypotheses. Then it uses this model to make predictions.
So the model-based approach is like building a theory from data. Géron uses an interesting example, investigating if money makes people happy. Can you briefly walk us through that model-based workflow?
The author takes OECD data on life satisfaction and GDP per capita. They plot it, observe a linear trend, and decide on a linear model to represent life satisfaction as a function of GDP. This is model selection. The model has parameters, a bias term, and a weight for GDP. To find the best parameters, they define a cost function, like mean squared error, to measure how bad the model's predictions are. An algorithm then trains the model by tweaking the parameters to minimize this cost function. Finally, the trained model is used to make predictions on new data. This is a typical machine learning project workflow.
Nice,
That
nice.
neatly summarizes the process. Now, let's talk about what can go wrong. Géron highlights bad model and bad data as the two main culprits. What are some of these critical challenges?
Firstly, insufficient training data. Even simple problems often need thousands of examples, complex ones, millions. Then, non-representative training data is a huge issue. Your training set must accurately reflect the cases you want to generalize to. Géron cites the infamous Literary Digest poll of 1936, which wrongly predicted the US election due to sampling bias. Poor quality data with errors or outliers also hinders pattern detection. Lastly, irrelevant features, what's known as garbage in, garbage out, mean feature engineering is crucial, selecting, extracting, or creating useful features.
So even with good data, a model can still falter. What are the issues on the bad model side?
The main issues are overfitting and underfitting. Overfitting happens when the model learns the training data too well, even memorizing noise, and fails to generalize to new instances. Géron illustrates this with a high-degree polynomial model fitting noisy data perfectly, but making unreliable predictions. Solutions include simplifying the model, gathering more data, reducing noise, or applying regularization techniques to constrain the model. Underfitting is the opposite. The model is too simple to capture the underlying patterns, leading to poor performance even on the training data. Here, a more powerful model, better features, or reduced regularization might help.
And this leads to the bias-variance trade-off. Can you explain that?
It's a fundamental concept. A model's generalization error can be broken into three parts. Bias is due to wrong assumptions, meaning the model is too simple and underfits. Variance is due to the model's excessive sensitivity to small data variations, leading to overfitting. And irreducible error is due to inherent noisiness in the data itself. Increasing model complexity reduces bias, but increases variance, and vice versa. It's a trade-off you need to manage.
Finally, once we have a trained model, how do we ensure it actually generalizes well? How do we test and validate it effectively?
The only way is to test it on new, unseen cases. You split your data into a training set and a test set. The model trains on the training set, and its generalization error is estimated on the test set. If training error is low, but generalization error is high, it's overfitting. For hyperparameter tuning and model selection, you use a separate validation set. You train candidate models on a reduced training set, select the best one based on validation set performance, then retrain that best model on the full training set, and finally evaluate it on the untouched test set. This prevents data snooping bias.
And what if the real-world data is different from your training data, causing a data mismatch?
If you have limited representative data for production, like mobile app photos, but abundant similar data, like web images, you use a train dev set. You train on the abundant data, evaluate on the train dev set to check for overfitting, and if that's fine, you evaluate on your representative dev set. If performance is poor on the dev set, it's a data mismatch, and you'd pre-process the abundant data to resemble your representative data more. Only then do you evaluate the final model on the test set. And always remember the no free lunch theorem. No single model works best for all datasets. You have to make reasonable assumptions and test.
That's a thorough overview of the machine learning landscape, from defining what learning means for a machine to navigating the challenges of data quality and model complexity. Aurélien Géron provides a clear roadmap. If you found this discussion insightful, consider sharing it with someone curious about machine learning's foundational concepts.
Okay, share with your all friends that are very curious about machine learning. Okay, so going to start the quiz. Where the quiz? I think some issues there. Okay, I just mark it. Nice. Press F11. Go back. Go back. Okay, creating quiz and answering my question, and then I will move to chapter number 2. This chapter I will move.
End-to-end machine learning project.
Okay, now go to quiz. Make 15 question. Select chapters. Okay, you can select this chapter number 1. Okay, continue. Like 20 questions. And so from this question, you can skip this exercise. No question will be made from that. Okay, continue. Generate quiz. Now, while quiz is generating, I can see whether recording is proper or not. Yeah, recording is proper, display is proper. Okay, fine. Now, quiz is generated already almost. Almost done. Okay. So, starting the quiz.
What is the primary goal of machine learning?
Okay. Explicitly program every rule for a computer to enable computers to learn from data. Then create self-aware robots to ensure all software is in Python to enable computers to learn from data. Oh, yeah. In the context of machine
In the
learning,
context of machine learning, what is a model?
model is the part of the system that learns and makes prediction. It learns and makes prediction. And the person who programmed the system, there was a piece of other. No, the part of the system that learns and makes prediction. Which of
Which of
these?
these is a typical supervised learning task?
Clustering, classification, and anomaly detection. Dimensionality detection. This dimensionality detection, anomaly detection, and clustering are part of unsupervised, not supervised. Classification and regression are part of supervised learning tasks.
What is the primary difference between supervised and unsupervised learning?
The primary difference: unsupervised learning uses unlabeled data. Yeah, this is supervised learning is always more accurate. No, it depends on the data. Unsupervised learning uses reinforcement. Supervised learning requires human. No. Unsupervised learning uses unlabeled data. Okay.
Which type of learning involves an agent receiving rewards or penalties?
This type of learning involves an agent receiving rewards or penalties. Reinforcement learning.
What is the phenomenon where a model's performance decays because the world evolves?
A model performance decays because the world evolves. Nice. Underfitting. Overfitting. Because the underfitting. No. Model dropped. Model performance decayed because the first was okay, nice. What?
When is online learning preferred over batch learning?
Where when you never need to return the model? No. When you infinite when the system needs to rapidly changing data.
What is regularization in machine learning?
Casting model to make it simple and reduce overfitting. Increasing the number of hyperparameters. The process of creating new features. And the act of relating on the constraining model to make it simple and reduce overfitting. Regularization. Make it simpler and reduce overfitting. Why is feature
Why is
engineering?
feature engineering critical to the success of an ML project?
It ensures the system receives relevant and useful input data and removes the need for model. It guarantees 100% accuracy. It always automated by the computer. It removes. No, it ensures the system receives relevant and useful input data. Feature engineering. What is the
What is the
primary
primary danger of overfitting?
The system runs out of memory. The model is too simple to learn anything. No. The model performs well on training data but generalizes poorly. This is all fitting. What is the purpose of validation set?
What is the purpose of a validation set?
To compare candidate models and tune hyperparameters. To train the model from scratch, we replace the training sets entirely. To test the model after it finishes. To train the model from scratch. Propose a validation set. To compare candidate models and tune hyperparameters. Nice. Which of these
Which of these is a common method to avoid sampling bias?
only using data from one source, ignoring all outliers, and no, using only the most popular data. No, ensuring the data training set is representative of target use case. Okay. What is the
What
no?
is the no free lunch theorem?
There is no model that is guaranteed to work for best for every problem. Yeah. Nice. No free lunch. There is no model that is guaranteed to work best for every problem. What is
What
it?
is instance-based learning?
Learning by heart and using similarity to generalize. Training on million, building a global model, only using similarity to generalize. Only using building a global model. I mean, learning by heart and using similarity to generalize. What is the main
What is the
task?
main task in a regression problem?
Sorting data into categories. Regression problem. Predicting a target numeric value, grouping visitors, finding patterns and noise. Sorting data into categories. This is right. No. Predicting a target numeric value. In self-supervised learning, where do the
In
labels come?
self-supervised learning, where do the labels come from?
It is separate supervised model. Where do the labels come from? Human annotators, the data action, generated labels. Okay. What is the common way
Which is a
to
common way to
which is
evaluate model performance?
which is a common way to evaluate model performance? Guessing plus only checking out how long it takes to train using a test set. Guessing based on it only looking at the training data and checking how it look checking how long it takes to train. This is really a good question. I evaluate a model performance, checking how it takes to train. guessing destination, only looking for these two options, using a test set. Using a test set. What does
What
a
does a cost function do?
maximize the values how determines the model's name? Measure how bad model prediction are. Cost function. Maximizes the error neighbor. Measure how bad the model predictions are. So maximize here. Cost function. When does our underfitting occur?
When does underfitting occur?
When the model is too simple and to learn the error structure. Cross validation.
What is the purpose of cross validation?
To get more accurate performance by using multiple validation sets. So only two are incorrect. 90% correctly answered. That's cool. Thank you so much. Now you can generate more questions. Practice plot. Two questions are wrong. Was the main task in this is the predicting a target numeric value is the main task in regression problem. I answered this question for sorting data into it. No. This is clustering problem, not regression problem. And what is the phenomenon where model's performance decays because the world evolves? Model rot. Model rot. Model performance decays because the world evolves. Model rot. Okay, not underfitting. Okay, fine. That's nice, please. Now going to start chapter number 2, end-to-end machine learning project. Okay.